Okay, so as we go through the different layers of the internet and the protocols, um, let's just review thus far the layers that we've spoken about already with the internet. Okay, so thus far, we've talked about the physical internet, the wires, and the routers, and then we've talked about protocols around IP, right? Internet protocols, IP addresses, how we have to have an address on things. And then we've talked about the TCP, UDP. You don't really need to, this is in the last lesson, we really, talked about that. You don't really need to understand it in great detail, but the idea is that the TCP ensures that packets that arrive out of order are, that they're not lost and that they're reordered. And that's a transmission control protocol. That's this idea that packets come through in different orders. Packets get dropped, and then there has to be kind of protocols around how do we send a message back to the sending device that they have to resend certain packets. Okay, and that's why all packets include metadata like the IP address or the packet number to help move them through the network and reorganize them when they arrive. And that's, collectively, this is what makes the internet more reliable. Now, talking about the UDP protocol, you don't really need to understand that too much. It's not covered in the video, and you don't need to, have great understanding in detail. Really, the easiest way to understand the user datagram protocol is just that. So UDP is really more, when we're talking about when time is of the essence. So this would be when we're really just trying to get, live streaming or Zoom calls and things like that. There's really not probably much that you need to understand about it, and with specificity, you just need to know that that is the UDP protocol, just is kind of prioritizing speed over accuracy. Now, moving on to today's lesson, that's a bit of a wrap up from the previous lesson. Today's lesson talks about HTTP and DNS, and this would be the next layer of an internet protocol. So these are protocols, these ideas around, how do we continue to have bits and data transmitted successfully, okay? When you walk into a room, if I handed you, we'll just pretend that this is how we're going to do it. I will just be telling you as opposed to handing you a slip of paper. But I'm going to tell you what your IP address is. And we know that in order for you to communicate on the internet, you need to know the IP address of the other computer. So far, we've let you ask one another the addresses when communicating on the internet simulator, but this can be tricky. What I want you to do today is, you're going to create a list in your journal of everyone in your class's IP address. And here are the rules. You may walk around the room. You may share information with your classmates. You may talk or share information with only one classmate at a time. As you followed through with this activity, you'll remember that I was switching your IP addresses and as you were going around the room. And what I want you to try and think about is, why was I switching those IP addresses? And if the IP addresses can change, is there a better way for everyone to know everyone else's IP address? And what better way would there be? Just think about that for a minute. And if, we want to scale the internet to billions of devices, which there are billions of devices connected to the internet, then we need a better way to figure out one another's IP addresses. And this is what we're going to be discussing today. Okay, we're going to watch the video, and I want you to consider the following. How does the DNS solve the problem of translating domain names like example.com into IP addresses? How does the DNS help the internet scale? And scale is a really important concept. Give me a minute. Here we go.
IP address.
Most users never see or care about internet addresses. A system called the Domain Name System, or DNS, associates names like www.example.com with the corresponding addresses. Your computer uses the DNS to look up domain names and get the associated IP address, which is used to connect your computer to the destination on the internet.
And it goes a little something like this.
Hey, hi there. I want to go to www.code.org.
Yeah, I don't know the IP address for that domain. Let me ask around. Hey, know how to get to code.org?
Yeah, I got it right here. It's 174.129.14.120.
Oh, okay, great, thanks. Yeah, I'm gonna write that down and save it for later in case I need it. Hey, here's that address you wanted.
Awesome, thank you. So how do we design a system for billions of devices to find any one of billions of different websites? There is no way one DNS server can handle all the requests from all devices. The answer is that DNS servers are connected in a distributed hierarchy and are divided into zones, splitting up responsibility for the major domains, such as .org, .com, .net, etc. DNS was originally created to be an open and public communication protocol for government and educational institutions. Because of its openness, DNS is susceptible to cyber attacks. An example attack is DNS spoofing. That's when a hacker taps into a DNS server and changes it to match a domain name with the wrong IP address. This lets the attacker send people to an imposter website. If this happens to you, you are vulnerable for more problems because you are using that fake website as if it is real. The internet is huge and getting bigger every day, but the domain name system and internet protocol are designed to scale, no matter how much the internet grows.
All right. Okay, so now I want you to take a moment, write the answers to these two questions. After watching that video, I want you to write the answers to these two questions as an answer in Google Classroom. How does DNS solve the problem of translating domain names like example.com into IP addresses, and how does the DNS help the internet scale? And then you'll discuss with a partner. And now we're going to go to the final version of the Internet Simulator, and everyone's going to stay, if this ends up being a virtual lesson, everyone will stay in one main Zoom, and if we're in real life, then that's fine. There's no talking, okay? You're not going to ask anyone for their IP addresses, so you're going to go to Bubble 2 in Lesson 6, the DNS and HTTP, and go to the Internet Simulator. And then you're going to log on to this version of the Internet Simulator. There's absolutely no talking, particularly to get your partner's IP address. You're going to ask the DNS for the IP address of a user by sending get username. So you're going to ask the DNS for the username. Use the IP address you get back to communicate with at least 2 friends. You can talk about what you can talk about in your ideal world. What time would you start school? what would you eat for your perfect meal? And you're going to kind of communicate that way. But if you see, well, it'll make more sense when you go in there, but the ask is going to be specific, and it's going to be directly to the DNS. All right, and now we're going to watch another video, and as we watch this video, I want you to take notes on HTTP protocol. What is the problem HTTP is solving? What is the GET request, and what are you requesting? So we've already talked about DNS, now we're talking about HTTP. How does the HTTP rely on other layers of the internet? What problem is HTTP solving? Okay, so we're asking this again. Okay, I don't know, they need to really answer that twice. And what do certificate authorities do, and why are they necessary?
I'm Jasmine Lawrence, and I'm a program manager on the Xbox One engineering team. One of our biggest features is called Xbox Live. It's an online service that connects gamers from all around the world, and we rely on the internet to make that happen. This is no easy task, and there are a lot of things happening behind the scenes. The internet is totally changing how people interact and connect. But how does it work? How do the computers all across the world actually communicate with each other? Let's look at web browsing. First, you open a web browser. It's the app you use to access the web pages. Next, you type in the web address, or URL, which stands for Uniform Resource Locator, of the website you want to visit, like tumblr.com.
Hi, I'm David Karp, the founder of Tumblr, and we're here today to talk about how those web browsers we use every day actually work. So you've probably wondered what actually happens when you type an address into your web browser and then hit enter. And it really is about as crazy as you can imagine. So in that moment, your computer starts talking to another computer called a server that's usually thousands of miles away. And in milliseconds, your computer asks that server for a website, and that server starts to talk back to your computer in a language called HTTP. And HTTP stands for Hypertext Transfer Protocol. And you can kind of think of it as the language that one computer uses to ask another computer for a document. And it's actually really pretty straightforward. If you were to intercept the conversation between your computer and a web server on the internet, it's mainly made up of something called GET requests. And those are really very simply the word GET and then the name of the document that you're requesting. So if you're trying to log into Tumblr and load our login page, all you're doing is sending a GET request to Tumblr's server that says get/login. And that tells Tumblr server that you want all of the HTML code for the Tumblr login page. So HTML stands for Hypertext Markup Language. And you can think of that as the language that you use to tell a web browser how to make a page look. So if you think about something like Wikipedia, which is really just a big, simple document, and HTML is the language that you use to make that title big and bold, to make the font the right font, to link certain text to certain other pages, to make some text bold, to make some text italic, to put an image in the middle of the page, to align the image to the right, to align the image to the left.
The text of a web page is included directly in the HTML, but other parts, images or videos, are separate files with their own URLs that need to be requested. The browser sends separate HTTP requests for each of these and displays them as they arrive. If a web page has a lot of different images, each of them causes a separate HTTP request, and the page loads slower. Now, sometimes when you browse the web, you're not just requesting pages with GET requests. Sometimes you send information, like when you fill out a form or type a search query. Your browser sends this information in plain text to the web server using an HTTP post request.
So let's say you log into Tumblr. Well, the first thing you do is you make a post request. That is a post to Tumblr's login page that has some data attached to it. It has your email address. It has your password. That goes to Tumblr server. Tumblr server figures out that, okay, you're David. It sends a web page back to your browser that says, success, logged in as David. But along with that web page, it also attaches a little bit of invisible cookie data that your browser sees and knows to save. And that's really important because it's really the only way that a website can remember who you are. And all that cookie data really is an ID card for Tumblr. It's a number that identifies you as David. And your web browser holds onto that number. And then the next time you refresh Tumblr, the next time you go to tumblr.com, your web browser knows to automatically attach that ID number with the request that it sends over to Tumblr server. So now Tumblr server sees the request coming from your browser, sees the ID number, and knows, okay, this is a request from David.
Now, the internet is completely open. All of its connections are shared, and information is sent in plain text. This makes it possible for hackers to snoop on any personal information that you send over the internet. But safe websites prevent this by asking your web browser to communicate on a secure channel using something called Secure Sockets Layer and its successor, Transport Layer Security. You can think of SSL and TLS as a layer of security wrapped around your communications to protect them from snooping or tampering. SSL and TLS are active when you see the little lock that appears in your browser address bar next to the HTTPS. The HTTPS protocols ensure that your HTTP requests are secure and protected. When a website asks your browser to engage in a secure connection, it first provides a digital certificate, which is like an official ID card, proving that it's the website it claims to be. Digital certificates are published by certificate authorities, which are trusted entities that verify the identities of websites and issue certificates for them.